So in this video, we're going to be finding the exact area under the curve, not an approximation anymore, by using the limit definition of our definite integral, which is basically we're going to find some Riemann sum and then take the limit as n approaches infinity. So let's start by doing a little review. So our first problem is x cubed. I've already got it drawn, and we're going to go from -1 to 4. And we want to do 5 subintervals. So I've already got it set up with a width of 5, so we can easily break them down into 1. But we already know our delta x, remember that's our b and that's our a, would be b minus a over n. And so all we're doing is plugging it in, 4 minus -1, and we have 5 subintervals, and that gives us a width of 1. Now notation-wise too, we always call, since this is a right side, our first point would be here, our second point, third point, fourth point, and then fifth point, because it's a right side. So that would be our right, and then we would move to the right. So next right, and then move over, next right, that one. And again, that just gives us all of our areas. So now we would know that our actual area is our delta x times all of our functions. So f of x sub 1 is our first height, f of x sub 2, f of x sub 3, and then f of x sub 4, and f of x sub 5. So it's our width times our heights, right? That was how we did it before. And that would give us the area of our approximation. So we know our delta x is 1, and then we're going to be plugging in what each one represents. So our x sub 1 is 0, x sub 2 is 1, 2, 3, and 4. So we're going to plug in 0, 1, 2, 3, and then 4 into our function to get all of our heights. So this is just a cube, so we're just going to cube each of those x values. So 0, 1, 8, 27, and 64. And then adding all this together would give us our actual thing. So this is the sum of all of our sum of all of our heights and our height. So if we add all those up, we get our approximation. So this would be 1 times 100, which equals 100. So we're going to be doing the same exact steps, except we want to make sure that we find not an approximation of the area from -1 to 4, but an exact area. And so that's what this integral means. We're taking and finding the area under the curve of x cubed from -1 to 4. So that means our function f of x here is x cubed, and our interval is -1 to 4, given that integral. And so that's going to equal, that integral will equal the limit as n approaches infinity of the sum of all of our little rectangles that we have. And then these are what we already know. So delta x is b minus a over n. We knew that one. And this is the new one, our x sub I. And if you think about what it is, what this is saying is your x sub, let's just plug in 1, is our first value of our interval a. In this case is -1. So we would end up with 1 delta x away. So our a here is -1 plus, and then our delta x was 1, right? So -1 plus 1 is 0. So you see that's our first point. So it's just a formula to create all of them. Let's do another. So we did 2. Our first value is -1, but now we're going to go 2 delta x's away, and you see that's now 1. So this one is 0. This is 1 delta x away, 2 delta x's away, 3, 4, and then 5. And that would give us all of our x sub i's. Now we're going to be going off to infinity, and so that's why we have this here. And so there's going to be a lot of them. See, our I is at 1, and then we're going off to n, but our n is approaching infinity. So what happens is this. Our 5 subintervals become, well, let's just go there. Let's just make them a lot bigger. Our 5 become an infinite. And so see, right there is at 200, and it's almost completely filled in. So what we're doing is taking our n, the number of rectangles, and setting it off to infinity. And by doing that, we are filling it in. So that's all this means. Limit as n goes infinity. We would now get an infinite number here, and you can see that our n is a denominator here, so this guy is getting smaller and smaller. Look how little his width is. So as n goes to infinity, you can actually see that the delta x is approaching 0, that our width is approaching nothing. It's becoming like a super thin hair, and thinner than you can think of that. So let's try one. Well, the same one. So we have our approximation up there. And so now what we're going to do is find everything just like we did before. So we got to find our delta x. We got to find our x sub i's. And then we're going to take each of these x sub i's and plug them in. And then we can write out what we need. So first, delta x. So our b here is 4, and our a is -1. So this would be 4 minus -1, just like before, over n. And so it becomes 5 over n. And we know our a is -1. The I is not going anywhere. Remember, the I is what we plug in. So that gives us first point, second point, third point, fourth point, fifth point. And it's going off to n, which is going off to infinity. So you can't get rid of I. I needs to stay. It's part of our formula. Our delta x we now know is 5 over n. So we can plug that in. So now we have a formula to create x sub I. So what do we do with those x's? Well, we plug them into our function so that we can find out the heights of our rectangle. So far we know our width of each rectangle. Now we need our height. Okay? So we plug those in. So our function f of x is x cubed. And so this is really going to become x sub I cubed. You can see I have x sub I. So all I'm doing is replacing the x with x sub I. Now I can take what I know as my x sub I and plug it in. So we end up with -1. I'm going to switch those two and put the I on the outside and the cube. So now all we need to do is expand that. So we're just using a little binomial expansion. So our coefficients for the cube were 1, 3, 3, and 1. And then now I can plug it in. So -1 cubed, -1 squared, -1. And then 5 over ni cubed, 5 over ni squared, and 5 over ni. Plus, plus, and plus. And so the first one would become just plain old -1. And then this would become 15 over ni minus -75 over n squared I squared. So that would be 25 times 3, which is 75. And then n squared and I squared. All right, plus, and then that's 125, and then everything in there gets cubed, so n cubed, I cubed. Okay, now we have everything we want. We have our width, and we have our height. So if you just think about it, all we're doing here is taking and adding up all of the areas of those little tiny rectangles. So width times height. So we're taking our height, multiplying it by our width. And so we end up with this, the limit, as n approaches infinity, of the sum of I equals 1 to n. And then we can plug in our f of x sub I. So that's our -1 plus 15 over n I minus 75 over n squared I squared plus 125 over n cubed I cubed, like that. And the reason this is so much more complicated is because I started us off at -1, which means this is -1, not 0, binomial expansion. All right, now that's just the height. We still got to multiply it by the width, which was 5 over n. So you can see that this is the same thing we have up here. That's our change in x times the addition of all of our heights. So there's our change in x, our delta x, times our f of x sub I, which is all of this. And the I just means we're going to plug in 1, just like we did here, and it's going to give us our first point, which would give us our first height. And then by plugging in 2 and 3 and 4 and 5 and 6 and then all the way to infinity, we get all of them added up, which gives us that nice area underneath. All right, and so we're going to distribute that 5 over n now. So limit as n approaches infinity of the sum of I equals 1 to n. And then we distribute. So -5 over n plus 5 times 15 is 75 over n squared I. Minus 5 times 75 is 375. Yep. n cubed. Now, on each of these, there's always going to be the n that is one exponent more than the I. So that's so you can tell everything's going well. 5 times 125 is 625. And the nice thing is I'm going to show you something in your calculator at the end that you can use to double check your work. So now what we're going to do is separate them all up. So limit as n approaches infinity. And then this is the sum of I equals 1. So we're going to distribute the sum across the sums, like we've done with our sum notation. So if you need to remember how to do this, just watch that video. So I equals 1 to n, and then that's I. And so I'm just pulling out the things that don't have i's, the coefficients with no i's. It just sounds creepy, huh? So if it doesn't have i's, take it out. Well, coefficient-wise, not just out of the whole thing. So this is just being multiplied to that. And so there we go. Okay, now we can just use our formulas. And I'm going to show you some tricks here to make this a little bit cleaner and quicker so you don't have to do as much algebra. So the first one is just our constant. So you see the constant here, we just multiply them together. So that's Cn. So this would be negative 5n times n plus. And then now we just write our formulas. What's the one for I? It's n plus 1 over 2. And then this one is n plus 1, 2n plus 1, all over 6. And don't freak out. Like I said, I'm going to show you how to make these very quickly and cleanly. Remember, we got that n to infinity. So we're going to use it. All right, so remember, we're trying to find the area under the curve. This will be a number. So all of these n's are going to disappear. So the first one you can see just cancels, and you end up with negative 5. And then it's plus, minus, and plus. Now what we're going to do is rewrite. So this is 75, and n plus 1 over n squared. And then this is 375 over 6, and n plus 1, 2n plus 1 over n cubed, and you can see how they're nicely matching up. I'll show you why in a minute. Just rewrite them now. Okay, so what's going to happen here is we're going to divide everything by n, and n squared, and n cubed, and n to the 4th. So if you think about the denominator here, this is just n times n. So what we're going to do is divide everything, or basically divide these n squareds into the top. So it looks like this: negative 5 plus 75 over 2. Why didn't the 2 right there? I don't know why. Perfect. Let's go back and double check them. 75 over 2, 375 over 6, 625 over 4. Looks good. So those little n's are going to go up there. So what we end up with is this. You end up with n over, and then inside it'd be n over plus 1 over. And I divide the n into both. So you can see I'm giving, this is n squared, I'm giving 1 n to this one, and 1 n to these two. So it's distributed nicely. If I were to factor out that 1 over n, I would get 1 over n squared. Now we move on to the next one. And then we do the same thing again. So this would now be n times n times n. So I'm going to give 1 to each. So this is why that I was telling you earlier that it has to be one more than the other to make sure everything is right. And so we're going to divide every single one of them basically by an n. And it works every time. So each part is just going to be divided by n, like this. Plus, and then 625 over 4. And then we're going to get, again, there's n squared and n squared. Come on, red. N squared, n squared. So I'm going to give an n squared to each in this one. Okay, so it looks like this. This is n squared over n squared. And then in the parentheses, you have a square already sitting there. So I can just put n and n. And so that would now be n squared times n squared is n to the 4th. So now a little simplifying and then applying the limit, which I haven't written yet. The limit as n approaches infinity. The limit as n approaches infinity. We can't get rid of that because these are limits, not functions. Okay, so now we end up with negative 5 plus 75 over 2. This cancels, and we get 1. 1 plus 1 over n minus 375 over 6. And then again, cancel. So that would be 1. And 1 plus 1 over n. And then 2 plus 1 over n. See, those cancel too. Plus, see it all forming nicely now? Cancel. So 1. Cancel 1 plus 1 over n squared, and then now we apply our limit. So you go to 0, you go to 0, you go to 0, and you go to 0. So now we can just rewrite our answer. Negative 5 plus 75 over 2, and then times 1 times 1. I'm going to write it. minus 375 over 6 times 1 times 1 times 2 plus 625 over 4 times 1 squared. And if we plug all that in the calculator, we get 63.75. And now I say we can check this very quickly in the calculator. So to check this in your calculator, you just hit math, and you'll see number 9, and there's our integral. So we just have to enter in what was given to us, the integral that we're trying to find. So it's -1 to 4, so you put in -1, scroll up and put 4, and then x to the power of 3, and then very important to make sure you tell it what the integral is respect to, which is x, and you hit enter, and it says 63.75. So if it didn't match, we would be wrong. Now, this method is really long. It's new. We're going to be able to do a definite integral much quicker when we enter the next section, but you still need to get through this process because what it's trying to do is get you to understand what you're doing, which is that you have first taken some Riemann sums here, and then now as you take the limit as it approaches infinity, it is giving you the area under the curve. So it's that two-step process, finding the rectangles, infinity. Rectangles, infinity. So when we do some applications of this, once you know what that rectangle is, you can see it sitting right here, or any of these rectangles. Right there, once you know what one rectangle is, all you need is that one rectangle so that you know that this is delta x, and then that is just your height, which is the y value of all those x values. So if you can draw one rectangle, you can figure things out very, very quickly on what integral to use. So if you just look at our integral, it's the integral from -1 to 4 of x cubed dx. Remember, this is our delta x, and this is our height. So this is our width, and this is our height. So all it really is the integral of height times width from -1 to 4. So it's a very quick little summer. That's what our little s is for. Thank you.